Good evening. I'm Ron Schreiner. I want to thank everybody for being here. I have been very honored to be invited to come speak at this group. There's been a lot of pretty high-profile people speak here, so this is a really good thing for me. My topic tonight will be on quantum tool chains now and in the future, and we'll take a little trip down the history highway and basically wind up with what can we imagine the future to be. So as we go along in this presentation, I don't have any problem with people popping up with questions. I'll try to keep an eye on the chat, but if not, you guys can just break in. I like the fact that Kevin's group has always been an open discussion, and I think that's a good thing to do. So getting started. Earlier this year, I attended a set of online sessions hosted by a Southern California university regarding quantum projects around the country and around the world. At that conference, I remember hearing a professor, possibly a professor from Yale, make the following statement: "We are in the vacuum tube stage of quantum hardware." Now, the more I thought about this, the more I realized it was pretty true, given that vacuum tubes might just be considered as the first quantum devices, even though they weren't exploited for their quantum mechanical properties. Also, both the vacuum tube and current hardware qubits were and are right at the beginning of their respective eras. So they have a lot in common. And so I found that statement to be pretty accurate. So tonight, we'll be taking a high-level flight over toolchain country. With a look at the past, the present, and the possibilities for the future. Along the way, we'll also touch on the technology of computer languages. As you can see, our agenda tonight starts with a brief look at history. We'll then quickly go over the current computing languages and compiler technologies that are in use today. Moving on, we'll get a snapshot of the current state of the quantum computing. And then we'll get to the fun part. We'll toss around a few ideas and try to imagine what the future might bring. To wrap up tonight, at the end, we should have time for open discussion and sharing of ideas. So with that, we'll move along. Who among us has heard the phrase, or hasn't heard the phrase, "Those who ignore history are doomed to repeat it"? With that in mind, I will start our history tour with the first electronic computers. When they came out, there wasn't a whole lot of software to support them. The phrase "whole lot" may even be generous here. Even the term programming here might be generous, as getting one of these beasts to run a single computational job required a team of people and quite a bit of time. On this slide, you can see in the upper left corner is a picture of the ENIAC computer. I'm not sure if this is a model or if it's actually one of the original device. It's sitting in a glass cage at a computer museum somewhere in Pennsylvania. But if you notice, it's got a lot of wires hanging out of the front, a lot of what appear to be switches and jacks, knobs and plugs. Looks more like a telephone switchboard than it does a computer. Also, if you notice in the background of this slide, there's an image of what was used as a setup sheet for setting the ENIAC machine up to run a job. And this, I looked around, I found this while I was searching for pictures. It's not the greatest resolution, you can't really read it, but if you look in at that background image, it sort of from a distance, looks like a quantum circuit timeline. So it seems like what goes around comes around. Or did we just come for full circle? At the bottom, we see what were then called programmers. They were, for the most part, ladies who would follow one of those setup sheets, go into the computer cavern, and it was cavernous. They were huge rooms, to set them up by throwing switches, plugging in patch cables from point A to point B, and turning knobs, basically doing a lot of mechanical things to configure that big machine to run a single algorithm or job. Back then it was like software. Who needs software? So moving on, we're going to go right straight to microprocessors. Now I know we're jumping over a whole bunch of stuff that happened in between the first electronic computer and microprocessors. In between, there were mainframe computers and the beginning of the mini computer era. And yes, the mainframes and minis started using high-level languages like Fortran and COBOL. C was in its infancy, but you did see it become available from companies like Digital Equipment Corp to run on their DEC computers. The one I had experience with was the DEC PDP-11. With the introduction of the Intel 4004, which is pictured in the middle here, and the 4004 is generally considered the first microprocessor, there wasn't a lot of software that came along to support it. It wasn't big enough to run the high-level languages found on the room-size industrial computers. After all, it was just a 4-bit CPU. I'm not even exactly sure what its address space was. Programming the 4004 may have started out as a tedious task of using a hex editor to sequence machine instructions and using some other mechanical mechanism to insert it into the memory device that was used as the stored program, which back then might have been an EEPROM or a ROM or some sort of non-volatile memory device. So you can see the 4004, it has a whole 16 pins on that package. Probably didn't need much more. Again, it was only a 4-bit chip. In the upper left, you see the 4004 chip. Some people refer to it as a die. It fit snugly under that gold cap of the 4004 DIP package. I don't know if this processor actually made it into production anywhere, although I've seen pictures of it in multiple package types, so it's possible Intel did make enough of them to go into production somewhere. In the lower left, we have the 8008. Now, the 8008 was an 8-bit CPU with a 16-bit address space. But if you notice, it only has 2 more pins. It only has it's in an 18-pin package. So Intel made a pretty big leap here, like doubled the size of their processor in a very short period of time. But turning either one of these processors, and specifically the 8008, into an actual functional product actually did require quite a lot of external support circuitry. You basically had to multiplex those pins to get things in and out of it, and that sort of provide external clocks, reset circuitry, that sort of thing. When the 8008 came out, it pretty shortly after it came out, they published an assembler for it. So some software showed up, and towards the end of its life, there was even my understanding there was even something called a tiny C compiler that could generate 8008 machine instructions from a very trimmed down C language. But once again, at this step in the history, we see that hardware gets released, jumps out in front of the software, and it takes the software some time to catch up. In the lower right corner of this slide, you see this nicely colored die, which the caption says it's also a 4004 chip, but I don't think it is. I just like the color, so I threw it on here. The next stop in our history journey, I'm going to jump to something that was called transputers. And one of the reasons is I've had some experience with this. They were early SoCs. or what we call today as systems on a chip, and they were provided by a company called InMOS. Their flagship product was, at the time, was the T800. In the lower right here, you see a picture of a pair of T800s mounted on a card with a NuBus edge connector. This card was compatible with Apple Macintoshes that were NuBus based or had NuBus backplanes. The T800 was a very interesting product, and you could build circuits with just the chip. It didn't require really a whole lot of external circuitry. It had a fairly large address space and a reasonably fast CPU. And if you didn't need a lot of memory, you could basically run these chips standalone. They had a minimal amount of memory built into them. And generally all you had to provide it was a reset circuit and or a reset signal and possibly some sort of external clock. Although I think even these early SoCs had an internal clock that you could default to. As you can see on this board, there's two of them, and they're both accompanied by a fairly big chunk of external dynamic RAM in the form of single inlines or SIP packages. The T800s had dynamic RAM controllers built into them. That was a very cool thing. So once again, with minimal external circuitry, you could build a functioning processing unit with a good chunk of memory, with a good amount of speed, and so forth. But probably the best T800 feature was that each of them had 4 bidirectional serial data pipes that allowed you to connect T800s together, sometimes in very large arrays. If you look in the lower right, you can see that you can configure if you look in the lower right, you can see that you can figure a set of 4 T800s in a ring topology and at the same time a crosspoint topology. Now, if we look back at the board again, we can see the blue connectors and the external connectors. The blue connectors via the patch cables that are right above the board allowed you to connect the T800s together or to those external connectors. The external connectors provided an outbound, inbound traffic lane so that you could connect this board to a very large array of transputers. InMOS had plans to build nodes as big as 10,000 cores or 10,000 T800s. Once again, software in this time, including algorithms, lagged behind because some of the things you had to deal with is the only way to get the power out of this device was to put a bunch of them together. Even though it was simple to build the hardware, it was easy to connect them together. You had to come up with topologies. You had to come up with mechanisms for getting programs, your algorithms loaded into a nest of transputers and getting them to do things. And, so once again, so what you wind up having one of the main problems is how do you keep 10,000 T800s busy? And it became a bottleneck in terms of how fast you could pump programs down the serial connections. You also had to worry about, there was no choice of what topologies would work best and how does the host computer keep track of what's going on 10,000 units. Some of the topologies that were tried was what I referred to as a folded binary tree, where you'd have 2 binary trees of transputers in a connected hierarchy side by side. One would be where traffic flowed down one tree, and when the traffic got done, it could transfer to the other tree and then flow back up to the top of the other tree and back to the host processor. But so that ultimately the transputer failed. It just didn't make it. Part of the problem was, again, software and algorithms weren't there to use it. Another problem was the end of the transputer was the beginning of the GPU cycles. So, and speaking of GPUs, this will be the last stop in our history visit. What's pictured on in the upper left there is the NVIDIA GeForce 256. It was the first GPU that they released. It was pretty amazing in its time, but it was dedicated to graphics processing, and the chips were only found on graphics cards. At the beginning of their life cycle, they they weren't easy. There were not easy ways to utilize the power of the GPU for things other than graphics, like say computationally intensive number crunching. There were people who did try things, but again, no software for support for just number crunching. So work was in that area was done by hand. Um, Now we take a big jump ahead in CPU technology, and we're going to look at the NVIDIA A100, which is shown in the lower left. A couple of things you should note here is that the GPU module is now on a separate board. That's because these things now get deployed in large clusters, and they've provided ways so they're not just on graphics cards. They can be deployed in large clusters and used specifically for machine learning or number crunching. A lot of work has gone on between the 256 and the A100, so it's a huge leap. But there were a lot of stepping stones along the way. A lot of things happened, like the creation of the CUDA framework, which allowed a mechanism to abstract away computationally intensive algorithms. Computationally intensive algorithms, and kind of offload the developer from worrying about how those things would get deployed onto the GPU. Once again, software and algorithms had to chase each other. Every time a new GPU came out, there was a lag. But we're sitting pretty good today with GPUs and utilizing the CUDA framework, which has evolved just as much as the hardware has over time. And these things are now cornerstones of the machine learning world, for example. Okay, we're going to slip out of the history a little bit. We already have, since we were looking at current. We're going to look ahead and see what GPUs are coming down the line. At the beginning of the year, I attended a NVIDIA Virtual Online Week of Technology and sat in quite a few sessions where they talked about how their main challenge was to find ways of getting the drivers and the algorithms in their frameworks to take advantage of their latest, greatest GPU, the H100 series. And there's an H100 shown in the center. And again, you can see it's on its own individual carrier board. So these things have switched over to a design that allows them to deploy on all kinds of things, not just graphic boards. But it basically came down to this new chip this H100 has so much power and performance that the problem is how do they keep it busy? This is a recurring problem. Does it sound familiar? It feels like a lot of effort is being extended to make sure software and algorithms are not so far behind the release of new GPUs. So the industry may be learning. And it seems like the lag between hardware and software does go down. And I think it's, some people are hopefully looking forward. So that kind of does it for history. The last comment is, will quantum computers be any different? Are we just one quantum hardware breakthrough away from leaving software in the dust again? Has the industry really learned the lesson? Are the software and algorithms lags at least getting shorter? This time around, we're not in a software vacuum, so we have that going for us. We have software, we have frameworks, we have libraries, we have a community of people. So hopefully, any new hardware breakthrough will be handled in a short amount of time as far as getting the software caught up. So we're done with history. We're going to now move along to current languages and compiler tech.
Yeah, I'm gonna
Um,
does anybody have any questions for Ron right now? So this is history. I saw there were some kind of comments in the chat as far as other people kind of living through this. For many of us, we haven't. But yeah, go ahead and you can unmute yourself, and then if not, give it a pause right now. Okay. Yeah, you can go ahead, Ron.
okay, so I feel it's very important to look at the current state of things, given the quantum has already prompted new computing languages on its own. As this graphic shows on this slide, we live in a sea of computer languages, and this doesn't even include a vast number of libraries and frameworks that each one of these languages have. Some would say that there are just too many languages. Others might say we are in good shape. One problem with there being so many is which one do you choose to learn? And because you really can't learn them all. Some people try. There's also the issue of which language to use for building frameworks for a new technology. Do you need to support multiple language with your framework? Can you just write your framework for Python? Is that going to be good enough? If the framework for your technology is written in one language, will you be able to interface with other frameworks for other devices written in other languages? So this ability to have so many languages raises some challenges in the compiler world. Moving on, so we'll take a quick look here at the current compiler technology that we live in. The main compiler suites I'm going to talk about are listed on the left here: GCC, LLVM, and Visual Studio. Although there's lots of compilers out there, I'm only going to concentrate on these because they tend to be generic suites, although GCC started out as a C compiler suite. That is to say that each of these suites have the ability to read in multiple different languages and generate code for multiple hardware architectures, which make them very flexible and extendable. So this is where you can understand that if you build a framework and you write it in one language, you can compile it to run in different hardware. That's a good thing. What is missing here is in just pure compilers is something that some people refer to as transpilers, a way to convert one language to another. The main components of a compiler suite are listed on this slide. Lexical analysis is the front end. That's what's looking at your source code. It's looking for things like numbers, strings, symbols, operators, etc. The tokens are then passed to the parser. The parser's job is to put those tokens together and create abstracts in a meaningful way to support the syntax and the semantics of the language, and to generate abstract syntax tree, or something people refer to as an AST. An AST is basically a hierarchical representation of the operations that must be performed to run your code. Note, a graphic representation of an AST is in the background of this slide, and it's just kind of sitting back there. It's just a very typical AST, and you can see it looks like a tree. It's got hierarchy. The key word in AST is abstract, which is important to the next phase, which is emitting. Emitting walks the AST, or the abstract syntax tree, and generates code for particular hardware architecture. Was there a question?
No, go ahead.
Okay. Some compilers so the emitter is supposed to generate code for a particular hardware architecture, which takes advantage of the aspect attribute of AST, because the AST doesn't care what hardware that this is going to run on. but it's in a generic form that can be emitted to almost any form of hardware. Some compilers, after the code is emitted, some compilers will have an optimization phase. This is basically where the machine code is checked, and if possible, it can be modified to improve the performance of the code on a particular piece of hardware. One such process was called peephole optimization, which could change the order of instructions to help keep the CPU busy all the time. Keeping the processor busy. Does that sound familiar? Also, optimization is starting to show up in the quantum world, having to do with issues with quantum algorithms. So it's interesting that this stack still kind of works, or works pretty well. So, okay, moving on. Take a real quick look at compiler technology. Let's say you want to build your own computer language. How would you start? Well, there's lots of standard tools out there that can help you do that. You could start by defining your language in what's called in a standard form that's referred to as Bacchus Noir form, which is a language used to define other languages. In the upper left corner, are you guys seeing my mouse?
It's really small. Yeah, we see it.
Okay. In the upper left corner is a sample of BNF. And if you guys can read the first line, it basically says a postal address is created by a name part, a street address part, and a zip part. And each one of those parts also have rules to define what a name part is. Actually, they go to the next line and you see what are the rules that define the name part. Same thing with street address and the zip part. There's rules in this language that tell you how to build those things. Once again, we have something that's very hierarchical, and but you have a way of defining what the semantics of your language are going to be. And the cool thing about this is that there are tools, and the most prominent ones were Lex and Yak. In the open source world, they became Flex and Bison. Lex is a general purpose lexical analyzer. The input to Lex looks a little bit like the BNF form. You basically create a listing of what makes up a token and feed it to Lex, and it generates a lexical analyzer for you. The lexical analyzer will extract tokens from the input and hand it off to the parser. Yak or Bison's job was to actually read BNF form, and in this case, it's very, very close to the actual BNF form, and take those tokens from the lexical analysis step, put them together in proper sequences to create statements or to create, again, an abstract syntax tree. Once again, in these days, we use Bison. Bison, its input is basically a listing like shown in the upper left corner there, and it generates code, usually in C, although actually Flex and Bison usually generate C programs, which you then have to compile and run. But I understand that both of them now have Python flavors, which is very easy to understand since Python does a good job at putting wrappers around C libraries. So again, once you have an abstract syntax tree, then you need some sort of program to walk the tree and do the real work of do the final phase of the compiler, which is to get some output. Whether that means generating machine code for some hardware. You can also use this technology to build transpilers. We can input one language and output another language, just by using these basic tools. Another common tool used for simple compiler building is the concept of recursive function branching parsers. These things tend to have their lexical analyzers built in. They're good for really simple languages. I've built a number of languages using this technique. They don't like to have ambiguous language definitions. They don't like to look ahead, have what's called look ahead capability in compiler speak. But they're really good at doing things like reading some pretty simplistic data, or reading a simplistic language and doing something with it. So, and again, these are all technologies that are in play today. So, and every one of these things on most of these slides, but particularly this slide, these are all presentations in themselves. So I'm really doing a high level view here. Okay, so now we can move on and look to see what is going on in computer country right now, or quantum computing right now. So this is just a quick overview of what frameworks are out there. I clearly, most definitely, probably don't have them all listed here. These are just the ones that I've run across and have had a peek into here and there. One thing that's interesting about these frameworks, as you can see in the upper left, the dominant framework languages are Python, C#, and JavaScript in that order. And as far as I know, I've only seen actually one framework written in JavaScript, and it has to do with a simulator called QC Engine, and I think it was just written to be an accompaniment. It was written as an accompaniment to an O'Reilly quantum computer book. So there's probably a huge gap between C# and JavaScript in terms of quantity. By and large, most of this stuff is written as Python language frameworks. C# is listed because of the Microsoft entry into the realm. Going past frameworks, as I had mentioned earlier, there are quantum-specific languages that are popping up. This is probably not a complete list, but as far as I know, and there might be one on here which is not really a language, but I didn't get deep enough into it to make the determination. But most of these are their own language, and they all set out to solve a different problem in the quantum computing world. Well, QASM and CQASM are actually languages designed to set up quantum gates or quantum qubits. Twist and QIWI are a couple languages that I've looked into. They both are high-level languages. They look similar to some of the other languages like SILQ, but they have different directives, and their optimizing phases do slightly different things. What would really be cool if some of these higher level languages would just get together and merge and provide these capabilities in a single tool. Going on from here, one thing we have to look at, we do have quantum computing tool chains out there. So we take a basic look at what goes on inside of a tool chain, and specifically a quantum computing tool chain. What are the basic components of the QC development cycle? Well, you're going to need to state the problem. The more you document that statement of the problem, probably the better off you'll be. Maybe this next step is to do some algorithm evolution, and you may be doing this in the quantum computing realm and in the classical realm, because let's face it, we're still in a very much of a hybrid environment these days. Once you get your algorithms worked out and some understanding underway of what you need to do, then you need to capture that understanding in code. This is where software tools come into play. When that's all over, you got to deploy this thing somehow. If you're actually working on a product that's going to actually use quantum hardware, you got deployment issues, and that they have to be dealt with. So we look at the first thing here, statement of a problem. And these are just a couple of things. There's probably more steps to this, but usually you classify the problem. Is it a decision problem, a search problem, counting, optimization? There's a lot of optimization problems going on in the quantum world. Are you just writing a function? is it a promise problem? And that tends to refer to asynchronous issues where you're trying to connect multiple things together. Next, you would go on to try to classify the complexity of your problem. This is more important with quantum these days because this is going to tell you what parts of your problem you may need to are going to be more likely that you're going to target at your quantum compiling resources. Of course, you need to document everything and use whatever engineering tools are out there, graphs, charts, maps, whatever you can get your hands on. So you've got your problem stated. You get on to algorithm evolution. And here we have, you got the one thing you got to do in quantum specifically or especially is do the math. You got to have your linear algebra, your calculus, know what a Hilbert space is, etc. You have access to algorithm building tools like pseudocode, universal markup language. There's also, all over the place, there's things that will simulate and visualize. One thing I'm going to show here is, hopefully this drags on. You guys can see this?
Yes.
Okay, so this is what I refer to as a better block sphere. But this is a device or a graphic where I think it just does a little bit better job. But you also notice it's got some texture and some shape to it. It wasn't this. Somebody put some thought into this. So this type of external representation could be very handy, especially in your quantum algorithm, to be able to actually see if you have this sort of tool and you can attach it to your simulation or to your algorithm research process, which might give you some much better feedback than some of the other tools that are out there. And again, this is just a block sphere, but I think it works a little better than some of the standard ones, or at least the one standard one, I should say.
Okay. Would you mind linking that in the chat?
Yeah, I'll do that at the end if that's okay.
Thank you.
That way, yeah, I won't close that. I'll keep that window on the side.
And then before we get too far here, there's a question by George. He asks, this is from before, it says, is that what we used to call recursive Dissent parser? And you can come on, George, to clarify or type in the chat.
Yeah, it's probably a similar name. I've never seen it called by that name, but
it was where the code you write actually reflects the BNF. So if you had like a block, yes, or an if then else statement, you'd have a piece of code called the same thing.
Yeah, you'd have, yeah, and the way I would implement those, I've written a couple in Python, and I actually implement using a metaprogramming technique where I just define methods in an object that have those node names, and I don't have to. Basically, the object knows, if I tell the object to implement a node, it knows how to find it inside of itself and implement that node. I've always gone with the recursive function branching because it's a recursive problem, but it's the type of problem where you have multiple functions and they can all call each other. So
yeah, it's where the BNF has a reference to the left side on the right side.
Yes.
Oversimplifying.
Absolutely, yeah.
Thank you.
Very cool. Another question, do we have QRAM from Madhu? Quantum RAM?
I have not heard of that yet, but that's one thing I can tell you, that going through this process of trying to put this together, and I've been collecting information for a few months now. Every time I run into somebody new or turn over a stone, there's 10 stones underneath it.
Yeah.
There's so much new stuff.
Is this equivalent to quantum memory, that they say that we can have like 20 seconds worth of quantum memory? It's really short time periods.
I believe Anna did a talk on a memory technique that people were working on using some sort of tuned cavity. I don't know that we got any information as to how long you could keep the bit in there, but I mean it made sense. You keep a photon in there. We speculated that since it's a tuned cavity, you may be able to pump it with a laser to keep it alive for a longer period of time. But
Yeah.
that's as close as I've gotten to it.
And then Anna, go ahead if you have anything. Also, Elias, his name's really long, but he says, as far as solving this whole, you know, processing large amounts of quantum data all at the same time, is that there's areas of quantum sensing that might help because due to the inherent nature of qubits and time, those types of things. And then if you have anything else, Anna, or go ahead, Ron.
Okay. Okay, so we'll move on to the stage where you've got to collect your knowledge and put it into code. So what are the tools that are currently available? We have text, which in that category you have the Jupyter Notebook, which shows up everywhere. It literally is everywhere in quantum land. It's in the IBM lab. It's all over Amazon. Or Google's Go Lab. But you can also write most of these languages you can write with your favorite text editor. So that's kind of a cool thing. Another area of interest is graphical interfaces where things like schematic capture, things that are akin to schematic capture of things like quantum circuits. And I have a window for that. I'll drag that over here. This is part of the IBM Quantum Experience, and I've been playing in the IBM Quantum Lab. I haven't used this one too much, but what you can see is there's a lot of stuff going on here. Actually, this is a little bit better than it was just a few years ago. But you can do things like grab gates, drop them on your timeline, and I'm assuming that somewhere, well, it's right over here. It builds the code in QSM, QASM. So rather than trying to write the code and then see what the circuit looks like, let's just build the circuit. So this is really a great step forward. Again, anybody can sign up for the IBM Quantum Experience. You just basically go to quantum-computing.ibm.com and set up an account, and there's all kinds of resources up there to help you along too. But again, the thing I wanted to show you here, we have a schematic capture. So instead of writing code, we're drawing circuits, and it's generating the code. When we go to run this, they do have a better block sphere output on here now. I remember seeing this a while ago, a couple years back maybe, and it wasn't quite as nice as this one. But so this is just one example of things that are going on. And again, future tool chains. Another thing about this is they have this circle notation over here also. The circle notation really helped me out a lot when I started going through that O'Reilly book, because that's the mechanism they use both in the book and in their quantum simulator, and it just made more sense to me. May not work for everybody, but it allowed me to gain more understanding over quite a few of the quantum algorithms. So I'll take that guy off. And again, I'll drop, well, this has got, I don't know if I can drop that URL in or not. It's got some stuff in it. Okay. And again, like I was mentioning, so the IBM Quantum Experience in their lab and their circuit builder is a great place to jump in right now. and it'll probably be the impetus for future toolchain enhancements, just based on what I've seen. And again, I'm listing the QC engine. This is something that what I'll do is I have the link for this somewhere. I didn't get it into the presentation, but it's an interesting place to play. It is a place on GitHub, or it's on GitHub IO, which is like GitHub's web pages. It's hosted up there, and it is connected to an O'Reilly book, so you can also get the book and go through it. So, moving on. Now you've written your code, you've done all the work. You have to compile, you have to get it deployed. The steps involved in deploying are you may have to do a final compile, because maybe you did your work on one kind of quantum hardware for numerous reasons, and now you're going to deploy it to something different. You may have to recompile things. You may need an optimization layer or device to get in between your code and the hardware, to take advantages of the hardware. Maybe some of these optimizers will, like I said before, all come together and deal with issues like one of the languages that I talked about, I think it was Twist. One of their features is that it identifies places in your program that may have had a unintended entangled state and flags them. One of the other languages had the ability to find gates that weren't needed and remove them. So that would be where this optimization kicks in. Also, when you go to run it, you probably are going to go back to the simulators again temporarily, and then you're going to finally do the final deployment to the actual quantum hardware that you're going to be using. The other thing that you should note here is, again, in the current environment, hybrids are the word of the day. So you're probably going to have to run two things here in parallel, the classical side and the quantum side. Are there any questions?
Any questions for the speaker? Go ahead, Dave.
Yeah, thanks, Kevin. Ron, that was a great presentation. I really enjoyed how you likened our era to the vacuum tube. Looking at your background on LinkedIn and what you went through, it seems that you're the guy who has taken things or understands it from the hardware side to the software side, including what I call microcode, which just might be a term I made up, referring to the code found embedded in circuitry. EPROMs used to be called, that sort of thing. Given that there's probably a hybrid photonic classical quantum chipset that might be coming out, and Kevin, you were actually alluding to that. I think it was last week or the week before. Ron, are you the type of guy that if given an experimental set of hardware that I described, that you could parallel what was done in the past and move it up to where it is, or sorry, to where it should be?
Well, the short answer is yeah, bring it on. I would hope I could do so. I would hope I have a lot of experience in a lot of different disciplines. It's interesting that you refer to it as microcode. One of my first jobs, I got labeled as the firmware guy because I was doing both hardware and software, and I actually became the arbitrator between the hardware and software group. Whenever they got into an argument, they came to me to settle it because I knew enough about both sides. So yeah, if someone wanted to get in touch with me and ship me some hardware, I would be more than ecstatic to give it a shot.
Okay, that's exciting. Just to close off on my comment, I'm creating an ecosystem amongst the large multinational hardware manufacturers and I'm looking to create a internal meetup so these manufacturers can become more knowledgeable about what's showing up. And I know they're putting a lot of money into these things. So I'll find you. We can communicate on LinkedIn, and I would love to present you as a technologist that could help put something together for them to guide them into what I think we're going to be seeing in the next few months.
I would be so up for that. So if we are connected on LinkedIn, that's great. We can start there. And I can, I don't know if
we are.
did someone drop my link? My LinkedIn is probably on the event page though, right?
Yeah, we'll put it in for you, Ron.
Okay. Yeah, I've only got like 50 windows going here, so. So we got one more thing to get through, and then gosh, this went 50 minutes already. So let's talk about what is the future going to look like. And these are just some ideas. There are some tools that are out there that are in play: interactive graphical algorithm building, about the manipulation of 3D objects, or enhanced user interface like virtual reality space. I'm going to go ahead and share one thing over here. I'm going to drag this over here, and this is code. Now I'm not going to pretend that this is a quantum tool. This AG code builder is something I built a while ago, and you can see it's, if you're familiar with the language Snap, or there's another one, I can't think of the name of it right now. These are languages that are kind of designed for children to teach them how to program, and you can see that there's logic elements in there, and you just basically pop these guys out and build programs. Well, I can conceive is I can just drag this thing around, and I'm going to like throw a Hadamard gate on there. I've got a qubit here that I'm going to start in state 0, or I could, let's say I want to start it at state 1, just to be difficult. Maybe I want to put an X gate after it, and when I get all done, I got a measurement. So maybe something like this. Now this is very simplistic, and I probably wouldn't waste much time on this, given what IBM has done. But basically, this type of technology at a much higher level, where you're snapping together algorithmic blocks and not just quantum circuits, might be something that will help the future. So something I just wanted to share. And I got to tell you, I spent all of 3 minutes building those quantum blocks in that system. So they don't have any brains behind them, but putting that together so I could snap them together for you was like nothing to it. So
yeah, and this is very, very helpful. So for those of you who are just coming on or have been on, so Ron went on this basically history of previous computing. It kind of reminds me of the homebrew computer club, those types of things. Now the two big things, the additional thing I picked up tonight, which is huge for everything, is Ron said hardware before software, and obviously with quantum we're the other way around. So that's the whole thing, is that there's so many different hardware technologies that could just break through, and all of a sudden we're hardware before software. So that's the theory that I have as well. Now the other thing is Ron mentioned documentation. Now, for those of you out there, you could be the best programmer in the world, but if you can't quote your work and write it down neatly for others to see, and this is if you win the lottery or get hit by a bus, if people can't reproduce your work, it has no value to the company. So it's a huge thing. Anybody that we haven't heard from, there's a number of people that usually come on here. So, and Vince, if you have something, go ahead.
Yeah, actually, Ron, I believe we had a sidebar the other day, and you recommended the quantum computing with Python book, and I actually got quite a bit of value out of that. I really appreciated the recommendation. It was like really nuts and bolts, and talked a lot about like how to apply the machine learning components and what was available, and some stuff about the tool chain, but more about like the data structures and like how it might actually look in a classical context to use these tools. So just wanted to thank you again.
Oh, well, I appreciate your feedback. I generally only recommend books that I've read cover to cover. So I was happy to recommend that. I know that the books out there now are coming in kind of two flavors. The ones that are more pragmatic, where they're not spending, well, they spend no time or very little time on any of the mathematics. And there's other books where they have all the mathematics you can handle and more to talk about all of, how the quantum stuff is happening at the quantum mechanical level. I think there'll be more books coming out where, again, it's just addressed at programmers. I mean, there's programming books out there, like for doing computational intensive stuff, but nobody goes inside the GPU anymore. They just know that this function will handle this a certain way, and it'll optimize itself once it gets over to the GPU and things like that. So, and I keep looking. So I also like to see people are reading books that they're popping those up for everybody to have a look at.
And there was a question in the chat. What is your favorite quantum computing programming language? And then we got 2 for Python. It seems to be very popular. It was really good that you broke down the frameworks and languages to those that don't do this every day. That was very helpful as well.
Yeah, as I think I mentioned, Python is clearly the dominant generic language used in quantum. Part of that has to do with Python has become the de facto scientific language. And its real claim to fame is that from the very beginning, they made it easy to reach out their arms and put wrappers around all the standard C libraries. So from day one, if you had a C library that had capability, it was immediately available in your Python script. There's a lot of other similar languages are at that same genre of language that they miss that step.
And I think you quoted, was it last week, of kind of the origin of Python? Do you want to share that again?
The origin?
Yeah.
I don't know if that was me. Like I said, I do say that from its beginning, it had a mechanism to put wrappers around existing C code.
Yeah, yeah, that's what it says, C code. Okay.
Yeah. So, and the main person driving Python in the last year or so has been in a combative sorts because there's people pushing him to move Python or to give Python features that he doesn't want to give them because he thinks they're not good programming designs. So it was one of those situations where he walked away from it. But Python is very mature. It's got its problems.
Okay.
There's a lot about it, but
so we'll give you a second to catch up if you want to put anything into the chat, Ron. And this goes for anybody out there. So David's asking, can somebody put in the Python for quantum book name here? Oh, okay. Vincent just did. So we're caught up. Now, I guess probably the last thing here is you said, how many of multiple languages do you need to support? So obviously the bigger companies kind of look at everything, right? And you had mentioned Twist. Is that kind of like mainstream now? Am I Twist?
I don't know that it's mainstream. When I first looked at it, I sort of got the feeling that it's a work in progress. I was looking for, the BNF listings for it to see what the semantics of the language were. They didn't seem to understand what that was. The guys who are doing QIWI are using the exact tool chain that I talked, or the compiler technology that I talked about tonight, and they're using Flex and Bison in the Python rendition of them. And so they're creating their language by defining the language rules in BNF, and but that's also it's in its infancy. I've made a connection with the compiler guy over there, so we'll see if anything happens.
Then I'm putting in the chat. So this is Ron's LinkedIn. So definitely check that out. I appreciate you sharing your nickname, the firmware guy. I'm sure that
I haven't used that in ages, but that was me, the guy in between the departments, and developed quite a reputation. So
yeah. Well, there you go. Any other last comments for our speaker tonight? If not, any other last remarks from you, Ron?
Well, I just wanted to thank you, Kevin, for inviting me to do this. I know you didn't ask me once. I just finally felt like, yeah, I know enough about this stuff. I can make a difference. So
Yeah.
here I am. And so thank you to you. Thank you for running this group and keeping it open discussion. I really enjoy it.
So for those of you who don't know, this will remain quantum, but definitely more medical flavor. The hosts that I'll be inviting will be next week, neuroscience. She works at University of Austin, and she's in a quantum computing programming lab taking her major is in neuroscience, basically. So that'll be the goal, because obviously that's where I'm switching into. Appreciate all the great the praise here in the chat. If you haven't had a chance, you can open chat, click on the triple dot if you missed some links, and then you can download today's chat. I'll stay on for a little bit here. So this has been episode 44 with Ron Schreiner, CTO of ACUMEDX. So feel free to reach out to Ron on LinkedIn. Thanks again, everybody, and have a good night. Take care. Bye.
Good night.